gentlemen. Thanks for sticking around. So my presentation today is called Neighbors, My Neighbors. My name is Kevin Stofan. I'm a customer-facing data scientist at DataRobot. I don't use spatial on my day-to-day now, but my background is in spatial, and I have some things I want to talk about in terms of that. I didn't want to give you a laundry list of things I've done or where I went to school and things like that, but I love this concept of a spatial data scientist. I work with a lot of machine learning practitioners, people who didn't necessarily come through a spatial background, and I do think that we have a lot to offer, in these machine learning workflows. I think a lot of us started off in the same place, GIS analysts, maybe you came from some kind of spatial science background. We're exposed to a lot of tools that a lot of other data scientists aren't exposed to. And when there's any spatial data or spatial relationships in these problems, I think there's a lot of value that we bring to the table. I really think that we're at an inflection point too. So there's all kinds of great libraries to conduct machine learning. We're doing all kinds of things to automate these processes. I think there's a point in time now where we can really embrace these things and add value to these workflows. I don't know. Maybe there's a track where we sort of excel in these workflows and become the leaders there, or maybe there's an imposter track where we go back to doing pivot tables and pandas and things like that. You might be wondering why I have a little bird on this slide. So I saw there was someone that's presenting from University of Liverpool. I don't know if he's here right now. But I thought if my presentation went south, my sons and I have become real big fans of English Premier League soccer recently, and I thought I would get at least one fan of my presentation if I put a Liverbird on here.
I'm a Geordie, so that's got more things.
I was afraid of that. I was afraid that you studied or that you worked there, but you're not from there. So hopefully you'll stick with me though. Anyways, a little background on this presentation and the title. You might be wondering what it is. I gave a lightning talk about 6 years ago titled Neighbor of My Neighbor, and it was really just a primer on using things like PySal and doing exploratory spatial data analysis to an audience that didn't really know how to do these sorts of things. It probably wasn't the right format for that. I think it was like a 5-minute talk with 20 slides. It was ridiculous. So this is a little better format. I've also given a series of workshops. They're mainly Jupyter Notebook based in the last 2 years that were presenting sort of basic spatial data analysis and how to incorporate spatial data into traditional machine learning workflows. And the audience there was mostly non-spatial data scientists. So I think one thing that I found very surprising, especially where I work now, where you have machine learning practitioners that have been doing this stuff for a long time, maybe not necessarily spatial data. Even the basic things, like if you go to maybe like the Kaggle, Zillow competition, you see some of the things in the threads and the forums there, just basic things that folks that haven't come with, with a spatial background just don't know about spatial data. So from those workshops, and this isn't anything really sophisticated, but I sort of laid out this geospatial machine learning workflow, and these things might be pretty obvious to a lot of us in the room, but I think that we offer a lot of things to each of these steps in the process. So things like geospatial data ingestion, there's tons of tools that we've been exposed to that we can use to help with that process. In terms of exploratory spatial data analysis, so you see a lot of data scientists that conduct EDA, but obviously there's a whole set of things we can do to analyze spatial autocorrelation and things like that in our data. But I highlighted 2 of these in particular. So one is defining the spatial structure or spatial relationships in your data set, and then also geospatial feature engineering. That's really what I want to focus on today. So if you don't, if you're interested in predictive workflows and using spatial data in predictive workflows, which some of you have mentioned it already, if you take one thing away and you haven't read this paper yet, I would suggest you go out there and take a look at that citation down there at the bottom. I think it's unique in that it lays out some very practical guidelines for making predictions in settings, whether it's spatial or temporal or other autocorrelation in the data set. So if you take one thing away from this, I would say go out there and read that paper and use it. I think it's unique also in its focus on predictions, so which isn't found in a lot of academic papers. Well, one thing I wanted to highlight there was this setting that I'm going to talk about here is, although they recommend group partitioning or blocking in terms of how you structure your training and test sets in your workflows, I'm kind of focused on out of sample predictions within the same study area. So not necessarily an extrapolation outside of the study area that I'm working in. So I sort of highlighted that because that's that context that I'm talking in here. So, most of you know these things. How do we define spatial structure or spatial relationships, in our study areas and our data? Some of them are, a lot of things you've seen, especially when you're doing exploratory spatial data analysis, is doing things like, a Rook's case or a Queen's case representation of spatial relationships. And it's really important, particularly in machine learning workflows, because the way you present that data to an algorithm or a model has long-term effects or deep, it really carries through the analysis. Another thing that I'm very interested in, this is really where the concept of my neighbors comes from, is not only looking at my immediate neighbors or relationships, but also specifying lag relationships or investigating lag relationships. So I've sort of been obsessed with this. You can see that, I've been giving presentations for a few years now on this concept, and I've really been obsessed with this. So a lot of times you see in an exploratory spatial data analysis, you're only looking at your immediate neighbors, but I've always been interested in these lag effects, particularly in real estate and human geography applications. So really what I'm advocating for here, and things that I've been experimenting with, particularly in automated machine learning workflows, is enumerating all of the spatial relationships that could potentially be occurring within your study area, within your data. So I'm a huge, I know it was referenced earlier, but I'm a huge fan of Spatial. I think there's some great things there. That tool's been around for a little while, and I think it's just a great tool. I know there's some folks here from that organization, so thanks for your work on that. But you could go, simply go to the page that talks about defining spatial weights matrices, in Spatial, and out of the box you could probably get 10 different ways to describe your study area, your spatial relationships there. And what I'm talking about here is a Rook's case or a Queen's case may be too simplistic. Maybe you don't know anything about the study area. I think when you're working in industry, a lot of times you're maybe seeing a lot of use cases and you can't get as in depth as you might in an academic setting. So you may not have any concept of what the spatial relationship is there. So what this slide's talking about is enumerating all of those different spatial relationships. So obviously there's a downside to that, right? There's computational considerations for that. So and maybe just something around the size of what I used here, which is a data set of about 10,000 records that has maybe 100 features in it. If you're looking at something like maybe defining all of those 10 different spatial relationship structures, and then analyzing 10 different lags within that, you could potentially be looking at 100 million separate calculations, 1,000 new derived features that you're adding to a model. So you're increasing the complexity of your models, but also there's computational downsides to that too. So I wanted to use a motivating example. I've used this data set over and over again. It's parcel data from Pinellas County, Florida. That's where I live. Specifically subsetted for the city of St. Petersburg, which is in the Tampa Bay area of Florida. It's a little bit selfish, so my family, we've grown out of our house. We've been looking for a house. It's a tight housing market. It's hard to say that here, in the New York area, but it's definitely a tight housing market there, particularly for single-family homes. So what you're seeing is a data set of all the single-family homes in St. Petersburg. And rather than doing, sort of the traditional regression problem where you're trying to predict what the sales price is of a home, like the Zillow's estimate challenge. Actually, that was predicting the error, as someone pointed out to me this morning. But rather than predicting the actual sale price of a home, I want to predict whether or not a home is even going to come up on the market. So the actual target variable here is whether a house was sold. So what I'm trying to predict is the probability of a house coming on the market in a certain, a certain future point. In this case, within the next year. Some of the predictors that are involved here. So obviously, if you've dealt with parcel data, most property appraisers have a ton of data associated with each of these parcels. So things like structural data, permits that were pulled prior to a sale or prior to the prediction point. But in addition to that, what I've done here is added all of these lag spatial relationships. Now, when you do that, obviously I talked about, creating a bunch of derived features. So in this case, I took only the numeric features just to get some numbers here and build some charts here. So I think it was something like, a little over 100 features that were created from an original data set of 70 or so features. And when you're expanding a data set like this and you're trying to analyze all of the possible spatial relationships and all of the possible lags, across all of your features, certainly you're creating a data set that has a lot of highly correlated variables. You're creating a data set or you're creating derived features that may not add any value to your model. So you need some way of sort of down selecting that or selecting what's important. The way I chose here is something called feature importance. So there's a couple of open source implementations of this in scikit-learn and R. They're referenced on the bottom of this slide. But really what the process is there is, you build a model with these features, and then you basically destroy the information one by one in each of those columns, and then look at the reduction in accuracy that happened with that. And then the inverse of that is the relative importance of each of those features. So you can do this, it's a pretty modest calculation, you can do this across a lot of features and get an assessment of how valuable these derived features are. And you can see actually one of the lag variables came up as one of the best predictors in terms of feature importance in this case. That was only in one model that I chose. One of the things that's important to consider though is that you are creating a huge set of highly correlated variables. So you're adding redundant information to the model. You can see that in the correlation matrix here. So across you're seeing that spatial autocorrelation structure between individual features as they across those lags in each of those little small boxes. And you have to have a way to sort of get rid of that information get rid of that redundant information out of your model. There's some easy ways, some out of the box things, like if you just go to scikit-learn, there's ways to do some feature selection that'll help out with that. Clearly, obvious things like just completely duplicate or replicate columns, are easy to get rid of. In this case, what you're seeing here are the results of just taking feature importance as that feature selection metric. So a couple other things that you have to consider. I talked about creating so many derived features and adding a lot of complexity to a model. So there's a lot of operational risk there in terms of creating all those additional features. And what we really want to do is reduce that back down to a manageable or optimal amount of features that we're using. One thing you can do, and my colleagues have done this extensively, this is sort of a simplistic version of that on one model that I built, but looking at the accuracy versus the complexity of the model. So across the horizontal axis, you're seeing the number of features in this particular model, and then looking at the gains in accuracy, as you increase the number of features. What you typically find in a lot of these things is, a lot of these models is there's some sort of optimal number of features that you can clearly see. In a lot of these, you can see it clearly. Here, it seems to be somewhere around 25 features. There's an argument that as you increase the number of features, there is some modest gains there, but you definitely have to weigh the operational considerations with having a model that's that large or that has that many features. Another thing to consider is, the amount of lift you're getting plotted against your computational speed. So there's a number of ways to think of the computational requirements for a model. If you're having to rebuild or do the feature engineering process over and over again as you train new models, maybe your environment's changing rapidly over time, you have to factor in the computation it takes to actually build those features. Then obviously retraining those models. And what I plotted here is actually the prediction speed. So You know, if you're in an environment where you're having to make, this isn't really that type of environment, but if you're in an environment where you're having to make lots of predictions, there's a high volume of predictions, certainly your prediction time is something that's really important. And what I've plotted here is you still see that accuracy on that top, on the top line there on the chart, but you're seeing the increase in prediction speeds. I think that was the time in milliseconds to score 1,000 records. And you're seeing that typically increasing as the number of features increases. So that's just another consideration when experimenting with this. One thing I want to point out is, so I did this across a large number of models, and in this case, the one that was the most accurate and was just based on a cross-validation score happened to be this XGBoost model. But I thought what was interesting is the final model here was the one that had 25, it took the top 25 features based on feature importance, and 10 of the 25 features were actually lag variables. So, you know, I don't think it's any surprise that these variables are important in the models, but I think if you go out there and you look at some of these you know, you look at some of these models that are built, or some of the competitions in CARTO and things like this, you know, these sort of lag features in a spatial context are you know, largely ignored. But there's certainly a lot of information to be gained from including them. A couple of things that I didn't really talk about and I didn't really experiment with. So I've largely ignored the time dimension here. It certainly adds a whole layer of complexity. There's similar things that you can do here in terms of you know, derived time features. So automatically creating lag variables in temporal space, things like that. One of the things that's worth considering here is, you know, taking an approach where you're using something like feature importance to select features. You may be missing out or removing important interactions in your data set. So typically those, at least the implementation that I use and the ones that I posted there, it doesn't have any consideration for interaction effects. So if you're just sort of you know, removing features from your data set, you might be missing out on those important things. So there are certain ways to discover and find interactions, and you know, alternative workflows might look for some of those interactions and then maybe prioritize those and not remove them, even though they may be lower on a feature importance list. And then another thing I certainly didn't consider here, since I kept it sort of random partitioning, is, you know, do these feature importance lists vary across, you know, are they going to change across models, which they certainly do, but are they also going to change across, you know, in time? So, you know, an approach like this may not always hold up in the future, and then certainly may not hold up in you know, when the partitioning scheme is different than what I use.